Good evening. We will solve this proposition, we will prove it. And the proposition tells us that in the first place, two matrices commute, and the origin for the pair A, the origin is an attractor of both matrices. Then we will prove that the origin is also an attractor of the sum of these two matrices. So to prove this, we will use this theorem that tells you that the origin is an attractor of some matrix M if and only if there exist two constants. This is positive and the other constant is more or equal than 1, such that the flux of M, the norm of this flux is less or equal than k1 or k times the exponential of minus mu with the norm of x for every x for every vector and for every non-negative t. So since the origin is an attractor of A and B, then we can assert that there are four constants, let's say mu1, mu2, which are positive, k1 and k2, which are more or equal than 1, such that, and we will have that the norm of the flux of A is less or equal than this here, and the same applies to the flux of B. And for every x, of course, and for every non-negative t. Alright, so we will prove this to the flux of A plus B. And this is by definition equal to this exponential times x. And since these two matrices commute, then we apply the property that tells you that, well, since they commute, an obvious corollary is that these two matrices also commute. Yeah, so the property tells you that if this happens, then this is equal to, only in this case, only when the matrices commute. Since they commute, then we can say that this is equal to an x. And now we apply the property that tells you that for every matrix A, the norm of this is a vector norm, is less or equal than the norm of A as a matrix times the norm of x. So we can perhaps write this like this. This is a vector norm, and this is the matrix norm. So here we have a vector. This is a vector because the exponential of a matrix is a matrix and x is a vector, so matrix times vector is a vector, and this is a matrix. So this will be less or equal or more or equal than the norm of the matrix, we write it here, times the norm of the vector. And here we apply this condition, so this will be less or equal than times k2, like this. And now the definition of the norm of a matrix, this is, let's say this is a matrix M. The norm of M is defined as the maximum of the vector norm of M times a vector V, such that V is unitary. So since this is a maximum, then there's a vector V such that there exists a vector V such that this norm is equal to M times this V0. This is by definition. And then we can say that this is equal to, let's, to make things even, let's just write it like this, times this v, times what you know. So we apply the condition again on the norm of this flux, because since it holds for every x, it will hold in particular for our unitary vector v. So this is also less or equal than, in this case, k1 times the norm of v, and we copy the rest. So we will write it more nicely. In the first place, this norm is 1 because this is a unitary vector, so we can forget about that. We write the constants on the left. Then the exponential of this times this is just equal to this one. Let me highlight it here. Times t and times the norm of x. Since k1 and k2 are more or equal than 1, then these, we can call this k0 is also more or equal than 1. And these two terms are positive, so their sum is also positive. And this holds for every x and for every t that is non-negative. So by definition, this implies that a 0 is an attractor of a plus v, because this is more or equal than the flux of this. So this is the proof of the part A, and for the part B we will use an analogous theorem. And let me copy to make it quicker. So part B. There's also another theorem that tells you that the origin is a repeller of M if and only if there are these matrices, but here the order is, and we divide. And also, instead of minus, we can write it with a plus. So this is on the characterization of repellers, and it's basically analogous. So we have that A and V and a repeller of, no, the origin is a repeller of A and V, then the flux of A plus V, which is equal by definition to this, is equal, since these matrices commute, is equal to this term. Then we treat this vector as some y. Then we apply the condition of that the origin is a repeller of the matrix A. Then this is more or equal than some constant k1 mus 1 t, and with a norm of y. But we replace this here, and then we apply this again. So this will be less or equal than some other constant in mu2 with times t with a norm of x. So we can write it like this, t times x. We could have applied this on the previous proposition. So yeah, this is more or equal than 0. I mean more or equal than 1. So we can call this k0, and this is positive, so which is mu0. Then by definition, this implies that this holds for every matrix, for every vector, and for every positive t. So this implies that the 0 is our repeller of the sum of these two matrices. So yeah, this is, I think this is all. Now seeing it like this, we didn't had to apply this property. It could have been faster if we just call this on vector y, but the result is the same. If you found this video interesting, please consider giving a thumbs up in the video and subscribing to my channel. If you have any questions, you can write it down in the comments below and I will try my best to answer them. Also, if you are interested in another topic that wasn't covered today, you can ask it in the comments and I will work on that. See you later.